This is the second video in a series on control for the online winter school on spectral methods for complex systems. In this video, I will be describing the pseudospectral approximation method for optimal control. So pseudospectral methods were first introduced to find solutions to partial differential equations. They were recently adapted for optimal control problems. The key ideas, given n as the number of discretization points in time, is to use orthogonal basis functions that result in spectral accuracy. Specifically, the coefficients decrease faster than 1 over n to the k for any k. Special recursive definitions for derivatives or orthogonal polynomials enable us to write the system dynamics as algebraic relations, and non-uniform node spacing enables optimal numerical integration using Gauss quadrature. So what do we mean by optimal control? Given a time interval, which we'll say without loss of generality can be mapped to the interval -1 to 1, we seek continuous controls U that will steer the state x between an initial state x0 to a terminal state x1, while minimizing a cost function j with a running cost L of x and u and a terminal cost phi, subject to dynamics x dot equals f of x and u and path constraints g of x and u less than 0. So the purpose of optimal control is to derive the minimizing control law U, and many applications exist in science and engineering. Indirect methods include calculus of variations, application of the maximum principle, and other analytic methods, but these are difficult to scale up to larger and more complex problems. Spectral methods are direct methods which enable us to reduce the optimal control problem in infinite dimensional function space to a nonlinear programming problem that can be solved using a optimization solver. So we would like to transform optimal control problems into constrained optimization problems. The unknown functions that we're solving for here are u and x, and we need to enforce the endpoint constraints and the path constraints. We will need to perform integration to evaluate the running cost objective, and we'll need to evaluate derivatives for enforcing the dynamic constraints. In very rare cases, we can derive analytic expressions for the integrals and the derivatives here. So the idea here is that we can use interpolation of the control in the state to obtain representations of these functions in vector space. We want to use quadrature to approximate the cost function, and we want to use spectral derivatives to approximate the dynamics. We'll then evaluate the path constraints at the time points on which we discretize the controls in the state. So here's an illustration of what we mean by discretization. So given some functions, we can sample the function, but if we try to then reconstruct the function from the samples, we may miss some of the features because of the infrequent sampling. So a couple convenient properties allow us to use polynomials to approximate continuous functions quite well. So Weierstrass's theorem asserts that the set of polynomials is a dense subspace in the space of continuous functions on a closed compact interval in the uniform norm. There's also an equal oscillation theorem in the corollary. It states that for positive n, the best approximating polynomial to a continuous function on the compact interval exists, is unique, and interpolates the function at n plus 1 points. That is, the polynomial interpolant the residual between a function and its polynomial interpolant is the minimum of all functions in this dense space. So given n plus 1 nodes that sample function, the nth order interpolating polynomial is unique. We denote this as I sub n acting on x. And I sub n acting on x, evaluated at the n plus 1 interpolating nodes tk, is equal to that function value at tk. So any interpolating polynomial can be expressed by the basis of Lagrange polynomials, denoted with little l here, where t0 through tn are the interpolating nodes. And the specific property of Lagrange polynomials is that their value at the value of the lth Lagrange polynomial at the kth interpolating point is the delta function Lk. So it's 1 if L equals k and 0 otherwise. So this is what the Lagrange polynomials look like. Because x of tk is the interpolating polynomial of x evaluated at tk, which is xk at the discretization nodes, we can say that x of t is approximately this can be approximated by this truncated polynomial series where xk are the coefficient values. This interpolation approximation is totally specified by the function values at the n plus 1 discretization nodes. So here are Lagrange polynomials up to order 7. So the important thing to take away here is that nodes need to be selected in a specific way for the approximation to be accurate. The polynomial interpolation is very sensitive to node selection. So Gauss-Lobato nodes are very close to optimal. And as we can see, if we compare uniformly spaced nodes to the Gauss-Lobato spaced nodes for interpolating this test function, 1 over 16t squared plus 1, we see that the Gauss-Lobato node approximation is far more accurate. So for the optimal nodes, we see that the error in the interpolating polynomial is bounded by bounded according to these certain rules. And we can prove that as the number of interpolating points goes to infinity, there is a certain order of convergence of the error in the approximation outside of the sampling nodes. So if we look at this error, we can see that for uniform sampling, the error outside of the interpolating nodes is much higher than for the Gauss-Lobato approximation scheme. And as we increase the number of interpolating points, we get a Gibbs-type phenomenon near the endpoints of the interval using a uniform grid where the error really explodes. So this shows the benefit of using Gauss-Lobato quadrature in spectral approximation schemes. Now, the scheme that we want to use is based on orthogonal polynomials. So given some weight function that's positive, whose integral is positive on the interval of interest, we can define an inner product of two functions, f and g, by integration of their product and the weighting function over an interval. So given the weight function, we can create an orthogonal basis of polynomials using a Gram-Schmidt orthogonalization procedure, where for this basis of polynomials phi k, we have the inner product equal to some value rho k only if k equals L, and 0 otherwise. So we can orthogonalize non-negative powers of t with respect to a weight function to get a set of orthogonal polynomials. So for such ways of generating polynomials, there are often systems of ordinary differential equations that the polynomials in the basis satisfy. Now, given a family of orthogonal polynomials, pk, we can express any function x of t as a polynomial series with coefficients x tilde k. So we call the polynomial interpolant of the function x Pn x, where n is the order of the polynomial series. So use of such orthogonal polynomials is what leads to spectral accuracy. That is, the kth coefficient decays faster than k to the 1 over q power for any q. And this is analogous to a Fourier series for a periodic function. So what this allows us to do is to recursively define the derivative as follows. And using orthogonal polynomials, we can express derivatives of polynomial interpolant functions as algebraic relations. Now, the Lagrange basis still benefits from algebraic relations for derivatives. So we can write the Lagrange polynomials in terms of Legendre polynomials, which follow this differential equation for generating the nth Lagrange polynomial. So the Legendre polynomials up to order 7 look like this on the interval -1 to 1. And we can use them for Gauss-Lobato quadrature. So given a weight function for a family of orthogonal polynomials for some n equals 0, we can find the optimal nodes as zeros of an expression of this form. So the weights for Gauss-Lobato integration will be integrals of the ith Lagrange polynomial times the weighting function. Now, Gauss-Lobato quadrature is exact for 2n-1 order polynomials, and this is very powerful because this gives high accuracy of when our optimal control problem is specified with a nth order discretization. Now, what we can do is convert our spectral collocation on Lagrange polynomial basis to Legendre polynomials. So essentially, if we take the polynomial interpolant in the Legendre basis Pn of x, and we take the original Lagrange interpolating polynomial In of x, we can map between the coefficients of the Lagrange basis to the Legendre basis using this matrix transformation M. Now, what we can do is examine spectral versus pseudospectral methods. So spectral approximations like Galerkin and Tau assert that there will be that up to the order n, the residuals of the approximation will be 0. So the same can be said of the interpolation scheme as well. So to summarize the elements of pseudospectral methods, we have spectral representation, interpolation, and quadrature. So Gauss-Lobato nodes are optimal for interpolation and quadrature. We use Lagrange polynomials for approximation and interpolation, and we can use an orthogonal basis that is optimal for quadrature for the spectral approximation and obtaining optimal collocation points. So applying this approximation scheme to several test functions, cosine and 1 over 16t squared plus 1, we see that third order approximation is not very good. The seventh order approximation is already quite good. 14th order approximation is very close. 21st order approximation has very, very small errors that we can't actually see looking at the plots. So recall again, the pseudospectral conversion is mapping from a continuous optimal control problem to a discretized finite dimensional problem that can be solved as a nonlinear program. So while we compute on the domain -1 to 1, we transform that domain to the time domain of interest between 0 and some time horizon t. Now the idea is that we express both the control and the state u and x using interpolating polynomials, and the decision variables in the optimization will be the values of the state and control solution at the collocation points. For Legendre polynomials, the weighting function equals 1. Now, interpolating polynomials use Lagrange polynomials, and the derivative rule is less obvious. So we want to express the derivative of the interpolating polynomial using a differentiation matrix. For the Legendre Gauss-Lobato scheme, it's given by these expressions where most of the entries in this dense differentiation matrix are ratios of the Legendre polynomials evaluated at interpolation points. So to summarize, in pseudospectral approximation, we want to expand a function x from some domain to R as a weighted sum of orthogonal polynomials. So let x bar k be the coefficients, and these polynomials will be orthogonal. Now, we have spectral accuracy, so the kth coefficient xk decays faster than k to the minus n. And we want to approximate a differential equation by algebraic equations. So for a truncated expansion, the residual is given as the derivative of the nth order approximation minus the function evaluated at this approximation. Galerkin methods require that the residual be perpendicular or orthogonal to as many of the basis functions as possible. Collocation methods require that the residual be actually zero at physically relevant points Ti. Now, in pseudospectral methods, nonlinear computations at collocation nodes involve operations on numbers rather than expansions. And the idea is that given an approximation of a continuous trajectory by a polynomial interpolation on a set of collocation points, increasing the order of polynomial approximation, the discretized approximation of the trajectory is exact collocation points, and the error will be reduced to zero as the number of approximating points goes to infinity outside of the collocation points. So the Legendre-Gauss-Lobato approximation scheme is exact for 2n-1 order polynomials, and the Lobato points include endpoints, which are convenient for enforcing initial and terminal conditions of the ordinary differential equation, dynamic constraints. So we can transform the time horizon for the optimal control problem to an interval -1 to 1, which is the Legendre polynomial basis support, and perform Gram-Schmidt on the positive powers of t using the weighting function 1 to obtain the Legendre polynomials. Now the roots of these the roots of the derivatives of the nth order Legendre polynomial are the optimal integration nodes. And Lagrange interpolating polynomials can be written in terms of the Legendre basis, and quadrature weights for the integration are given by integrating the Lagrange polynomials over the basis support. Now the differentiation matrix can be obtained where the entries are equal to the entry dik is equal to L of k evaluated at Ti. So the derivative of Lk evaluated at Ti, that is the derivative of the kth Lagrange polynomial evaluated at the ith collocation point. So why do we want to use all of these different polynomials? If we consider a function f of t, the Legendre expansion looks like this, where f tilde k are the expansion coefficients. These coefficients have no physical meaning. Now the Lagrange interpolating polynomials do have, so there the coefficients f bar do have a physical meaning, because those are the values of the interpolant polynomial at the collocation points. So interpolation is exact at collocation nodes, and therefore the triple Ti, Wi, Dik allows us to approximate fully any functions on the basis support, as well as integration and differentiation of any of those functions. So we can perform integration by quadrature using the quadrature weights, differentiation by applying the differentiation matrix to the function evaluated on collocation nodes, and we can approximate any function with a vector f of values at the collocation nodes that have direct physical meaning. And this allows us to translate optimization in function space to a nonlinear program. So we consider an optimal control problem with the states x controls u, and we want to minimize the running cost subject to dynamic constraints, endpoint constraints, and path constraints. And we can write this optimal control problem as a nonlinear programming problem where the objective is evaluated using quadrature. The dynamic constraints are evaluated using differentiation matrix at the collocation points on the time basis support, and the equality constraints and any path constraints are also evaluated along the path or at the endpoints. So here, again, we summarize everything on a single slide. Expanding a function on a basis support using Lagrange interpolants at collocation nodes tk. We can express any function using an orthogonal Legendre basis. We can generate then quadrature weights and a differentiation matrix to evaluate integrals and derivatives, and convert any optimal control problem to a nonlinear program. So while there is some complicated machinery to generate the scheme and to prove the order of approximation and convergence, application of this method is relatively straightforward. There are a number of software packages that can automate this, but it's also relatively straightforward to implement this oneself when solving any non-standard types of optimal control problems or approximation problems for ordinary differential equations. So that concludes the second presentation on control for the online winter school on spectral methods for complex systems. Some useful references for pseudospectral approximation and its application to optimal control can be found here. So spectral methods in fluid dynamics describes approximation techniques and convergence theorems, and the other references examine application of these schemes and to optimal control, as well as several applications in aerospace and other dynamic systems.